All right, I guess we are at time now. So there'll be people trickling in for the next 5 minutes, which is how the schedule works, right? My name is Taylor Campbell. I work on NetBSD. The slides, if anyone wants to follow along, are at this URL, at this QR code. This is not a code-heavy talk. Sometimes my talks are code-heavy, and people might like to browse through. But you're welcome to follow along at your own pace with your own copy of the slides. So on my laptop one day, I was just doing some NetBSD development, and I ran git status. And I thought, that's interesting. I don't remember deleting any files under GDB. I'm not doing any GDB development. Wait a minute. I haven't added any files either. And this is a very interesting file name. There's this directory external under NetBSD source tree for all the third-party software that we ship along with NetBSD, like GDB or GCC or libfido or any of various other things. That's a very interesting path name there. If you look at the difference between these two paths, the one that get things was deleted and the one thing get things was added, and you look at the octal representation of them, ooh, I caught a single bit error in the act with git, luckily in a place where I can detect it. I know what's going on. This is very lucky for me. But then I have to wonder, how many others did I not detect? Where else are there? Did I commit something into the tree that has some bit errors in it? Oof. Well, on this laptop, this very laptop that I'm using right here to present this talk, is about 3 years ago now. I had been catching a bunch of ZFS bugs, and so I'd filed some PRs with NetBSD to, these might be local bugs in our version of ZFS that I might have made a mistake with it, and so I filed these bugs as weird symptoms. I could not figure them out. This crash and SA handle destroy and ZFS inactive. This is not like in a NetBSD specific part of it. This is and maybe we could have made a mistake with this, but. And then another one in this red black tree code that has been working reliably for everyone for years. Like, how could this code have a bug? And in this arc decompressing, like, did we get a buggy zlib in our kernel somehow? And it's all sorts of PRs and. So I ran ZFS scrub. Did I screw something up and like is the kernel broken on this disk? Is the whatever? I ran some BIOS diagnostics for multiple days with the built-in Lenovo diagnostics in this ThinkPad, and finally narrowed it down to one of my two 32 gig DIMMs in this laptop. It takes a while to run these memory tests on a 32 gig DIMM. My laptop was out of commission for a few days as I was doing this science on it to figure out which one is busted. And then I submitted an RMA to Corsair, the RAM maker, and they received a replacement for both DIMMs within a week, and it was great. ZFS is great. I'm a big fan of it, but it doesn't help with memory errors. It can detect disk errors. If your SSD eats itself or the your spinning rust flips a bit somewhere, it can detect that with all the checksumming it does, but it doesn't help with RAM errors. And for that, you got to have working RAM, or you got to have some way to detect the RAM errors in your hardware. With this laptop, though, I don't know. I mean, the memory test diagnostics that I ran from the BIOS setup thing, they ran okay on the new DIMMs that I got. But if there's other memory errors, if a cosmic ray hits my laptop, how am I going to find out? So there's a few acronyms that are involved in the field of memory errors and error detection, error correction. So ECC is the general term for error correcting codes. This is how you can encode data in a DIMM, say, so that when you read it back, you can check was there an error. Or this is how you can encode transmission over a copper wire for Ethernet and detect if there are any bits flipped. Just general field of error correcting codes. Not all of the systems that you might be interested in actually correct the codes. Like in an Ethernet frame, there's a checksum, but if the checksum fails, you don't know which bit was flipped. You can't correct the code. So it's actually error detection and correction is usually what is more interesting here, or not more interesting, but it's the broader field of EDAC, error detection and correction. There are some codes where you can encode a data word into a code word, and then if it has been corrupted in some way, the code guarantees that provided the errors are independent and identically distributed, that is, each bit has equal probability independently of being flipped, a secdead code can correct a single bit error and detect a double bit error according to the most probable outcomes of this IID distribution on probability on bit errors. These are some of the acronyms that are involved. I'm going to say EDAC most of the time because that's more the term of art for the whole field when you're actually working in it. But I guess ECC might be more commonly recognized. You hear about ECC RAM. Nobody talks about EDAC RAM, but you'll see like EDAC drivers in the operating system for the DDR controllers error detection and correction. So a typical simple example of an error detection code is where you take a bunch of a data word that's n bits, maybe 8 bits or 64 bits, and you compute the parity. You just XOR all of the bits together, and then append the result to the data word to form a code word, which is a 65-bit or 9-bit word, and then you send that over copper wire or something, and the receiver can then recompute the parity bit, and if it matches, then it assumes, well, this is probably good, and if it doesn't match, then it determines, okay, this was probably a bit was flipped. Of course, if multiple bits are flipped, then all bets are off. But again, if we assume the bits are the errors are independent and identically distributed, then a single bit flip is the most probable error if there's any error. So it's a very simple form of error detection, but you can't tell what the error was. You can't correct it. Here's a slightly more complicated system of a Hamming 7.4 code. There's all sorts of families of error detecting and correcting codes. I'm not going to go into all the details. This is an example. If you're curious, you can find it on Wikipedia. There's some logic about how you can correct a single bit here. This isn't quite secdead. It can either correct and detect single bit errors, or detect but not correct single and double bit errors. And if there are 3-bit errors, then who knows? Lots of different systems out there. You can look up these keywords here if you're interested. There is no Galois theory in this talk, so for those of you who are afraid of that, then you can rest easy. So, as I mentioned, the basic assumption for EDAC systems is that errors are independent and identically distributed. There's a very dumb adversary, a monkey punching keys on the keyboard or flipping bits in your transmission to flip them at random uniformly. Now, this isn't exactly the right model for how the real world works. In the real world, you might have some bits in your DRAM there's a bad electrical connection. Those bits are going to have more errors. But if you take, say, a cosmic ray model and consider, cosmic ray comes and hits Earth, it might hit any one of your laptops uniformly. There's no reason that it will prefer one or the other, unless you're near Chernobyl or something, in which case you'd probably better have some pretty good radiation shielding for your laptops, depending on where you are in Chernobyl. Most of it's okay. But more importantly, out of scope for EDAC is an intelligent adversary. So we're not looking for an adversary who's deliberately trying to screw you up, who knows what system you're using, and who is trying to forge frames on an Ethernet, Ethernet wire. This is purely an unintelligent adversary. We're just looking for random errors. For intelligent adversaries, you've got to deal with cryptography, and that's for a different talk. There is also, incidentally, some cryptography based on error-correcting codes, like Michaelis, and it's sort of similar to lattice-based cryptography for other purposes, but that's, again, different talk. So what causes memory errors? There's high energy particles coming from the cosmos, from I don't know, quasars or whatever, or the sun. I'm not a physicist. This isn't my area of expertise. But they sometimes come through and pass through the atmosphere and hit your laptop. Or alpha particles, similar deal, especially if you're near radiation source, ionizing radiation source. Sometimes electromagnetic pulses. If lightning strikes and there's a power surge, or if you don't have one of those little wrist straps that you plug into ground when you're opening up your server and messing with it, you can go bop, and oops, you just zap something and flip some bits. Sometimes overheating. If the firmware in your server is screwed up and the operating system has to tell the fans to start spinning rather than having the operating system tell the fans to stop spinning, then if the OS crashes and you set it a debugger prompt and it's polling for input, running the CPU as fast as it can, but not running the thread that tells the fan to start spinning, then your temperature might start to spike and you might fry your RAM. I have seen this in practice. Or just faulty electrical connections if the soldering job is not quite right, or if one vendor once told us that when we sent a module back that had a lot of memory errors, they looked at it under an electron microscope and found that the ball grid array connecting the the DRAM module had a hairline fracture in it. No way we would have found that by eyeballing it ourselves, but that was one of the sources of memory errors. Errors can happen in many different places. There's spinning rust, which might, some magnetic force might trigger one of the hairs in it to flip, and however this works under the hood, I don't know. Or SSD might screw something up, or the DRAM module, or the memory interconnect, and then so anywhere in your system, there bits might get flipped, even inside the CPU caches or registers. But for the most part, I'm just going to talk about memory errors, partly because that's where I've seen most of them in practice, and the differences between most of these doesn't really matter that much for for the rest of the talk about how to deal with them and how to log them and whatnot. But there's a few some minor differences in all this. So, like, for example, ZFS can handle errors in the hard disk, but not in any of the other parts of this system. There are different kinds of severity of error. A corrected error is one where the hardware or maybe even software has used an error correcting code, and it has corrected the error, and so it hasn't lost any memory. But it might be interesting to know about, because if you have a bad DRAM module and it keeps having errors in the same place, even if you can correct them, that might be a sign that it is time to replace that DRAM module. Or that might be a sign that your firmware, the fan firmware, is screwed up, and you need to find a different version of the system so that it will fail safe and not fail in the flaming inferno. There are uncorrectable errors that can be recoverable or fatal. So if you have an uncorrectable error in a page of memory that nobody is using, just free RAM, it doesn't matter. You can just zero the page and it's fine. You can make progress. Or you can, if it's a page of memory that's used only by a single process or only by a single guest VM on a host, then, well, maybe it's worthwhile to just kill the process, kill the VM, kill the guest, but leave everything else running, because then, well, that's less downtime for everyone else. So that's a recoverable error. If you can identify exactly where the error happened and to be confident that it hasn't spread anywhere else. So some CPU architectures will provide guarantees about this, that if they report an error, they will say, well, we know that it is not propagated to any CPU register. It hasn't propagated to CPU cache or anything. Or they might tell you it has propagated, in which case it is fatal because you have no idea how many other places this error might have gone to and what else it might have tainted. So these are the three main categories of error severities. So the error correcting codes, error detecting codes, they distinguish between uncorrectable and correctable, but other parts of the system architecture can distinguish between recoverable and fatal errors. Then there's error persistence. So soft errors, alpha particle hits your RAM, flips a single bit. That's some random event. It doesn't have anything to do with your RAM itself. I mean, it might mean that you need more shielding on your RAM, but it doesn't have much to do with the particular DRAM module that you have in your system. Hard error is one where there's repeatedly errors in the same place, and that will indicate some electrical problem or overheating or something like that. So that will suggest different remediation depending on whether you keep seeing errors in the same place or not. And then error reporting. When the hardware detects an error, what does it do? And what was it doing? What were you doing when it detected the error? So in some cases, you have a CPU that will issue memory transactions. You run load and store instructions, and the load instruction will try to fetch from cache. It's not in cache. Try to fetch from L2 cache. It's not in L2 cache, and finally goes back to main memory. And in order for that load instruction to complete, it has to pass the EDAC check if you have a system that supports this. And if it doesn't, if there's a memory error detected in the course of that load instruction, you'll get a synchronous trap, and the CPU will know exactly what address was issued, exactly what instruction address was running, and what address, perhaps what address the memory error happened at, and you might have a single program crash when that happens, or. In some systems, there is a background scrubber that just goes through all the RAM from time to time and reads it out and checks all the ECC bits. And once it finishes the whole RAM, it starts over at the top and goes on. But this is asynchronously with respect to your program execution, with respect to whatever programs you're running, whatever operating system, whatever you're doing. In that case, or in other cases where, let's say you're sending a packet out on the network, and so you program a DMA controller to copy the memory out to the NIC, and that will happen asynchronously with respect to your operating system running, whether your program is running. And so in these cases, the scrubber or the DMA engine or something else going on in the system, you might get an asynchronous NMI, or maybe not even NMI. Maybe it's an asynchronous asynchronous notification. That there was memory error, but it doesn't have to do with any particular program. The programs keep running. You might not need to know, oh, this buffer that you were trying to do DMA on, that DMA can't complete. There's an error in it, so you'll get an asynchronous notification. So you might get high priority interrupts, NMIs or something, or you might get synchronous traps, like in ARM systems, a synchronous data abort, an S error, or you might get purely asynchronous notification at low priority, doesn't have to stop any programs running, and an operating system supporting all of this needs to handle all of these different paths in order to usefully report and log errors, because you want to know about the errors when you're trying to diagnose why your system is getting flaky, or make sure you handle it before your system gets flaky. So how do you know when you get a memory error? How do you log this? How do you find this in logs? Preferably not the way I did when I was trying to do some development. Preferably with a message in, say, dmessage or some other logging system that shows you this was a memory error. It was correctable. It was corrected, in fact, and well, this one doesn't tell me where it happened, but there's some information that's provided from the system firmware. This is from APEI, the ACPI platform error interface, and this is real output from NetBSD displaying an injected error, a simulated error. So how does this get from your hardware to the operating system? Well, So the DDR controller is a bit of hardware that talks to the DRAM module and talks to the CPU. And the DDR controller is often some, super secret NDA-covered device where you cannot download the documentation for the device registers. And even if you are working at a company that partners with a DDR controller maker, then they might, you ask them week after week, can I have documentation for the DDR controller for the registers to tell me the DDAC information? And they say, oh, yeah, we'll get back to you about that. And then 6 months later, they say, oh, so it turns out we do have the documentation. It's just that we had to go through our legal team to confirm that we're allowed to share it with you 6 months later. Very frustrating process. And then the vendor might also tell you, well, we have a scrubber. It's going to go through the RAM all the time, and it's going to correct anything, because a single bit error, there's low probability of that. The scrubber will detect that before it gets to a double bit error in the same word. A double bit error only matters, it's only uncorrectable if it's in the same word, same 64-bit word, say. And so the vendor might tell you, well, you're never going to see a double bit error, so why do you need to bother logging this stuff? Because it's not going to happen. We had a database of all the double-bit errors that we detected, hundreds of double-bit errors, thousands of single-bit errors on hardware we were doing testing on one place. The vendors, I think, eventually got tired of our reports back of, so we found more errors in the hardware you sent us that you told us we're never going to have these errors. There's been some research on the actual prevalence of memory errors. You can find, here's a citation here, there's some various other research on it, but it's so there's been some research about, so back in the 70s, there were some people discovered that there were enough alpha particles floating around in the world from space or whatever, that as DRAM got smaller and smaller back in the 70s, they actually had to put some shielding on it in order to not have errors all the time. So I think pretty much all DRAM modules have a certain amount of shielding that alpha particles can't penetrate. But more recent research has shown that there's also, these days, or at least 10 years ago, hard errors were more common than soft errors, so manufacturing defects in the DRAM modules, which of course is going to be more difficult as the RAM gets smaller and smaller. The physical size of it gets smaller and smaller, and the number of bits gets bigger and bigger. Now, in order for you to get reporting, the hardware has to actually support it. So there's a lot of DDR controllers out there that will support EDAC, but there's a lot of CPUs and a lot of ECC RAM out there. And so you might go and buy an AMD CPU, and pretty much all AMD CPUs, the big ones anyway, support EDAC. There's just this standard part of the CPU. There's stuff in the silicon to handle it. And you can buy, RAM that has bits for storing error-correcting codes, or EDAC, and you can put the CPU that supports EDAC and the RAM that supports EDAC into a motherboard that just doesn't do anything with all the extra bits you bought. They're just not. The wires aren't connected up. There are some in AMD CPUs. There's some MSRs, model-specific registers, just CPU registers, special CPU registers that will describe the EDAC support, whether the RAM supports it, whether the motherboard supports it, whether anything is using it, and it's kind of annoying to find the documentation for the CPU registers. On some models, it's publicly available. On some models, it's not. But you go dig down and query it and find out, oh, well, this machine I just bought the ECC RAM for, it's not doing anything. So in order to make sure that you will be alerted when an error happens, you have to dig through to verify that all of the hardware supports it and is actually using it. So it's not enough to just say, oh, well, I bought a CPU with ECC RAM that supports EDAC and RAM that's ECC RAM, and even necessarily a motherboard that is advertised to support EDAC. You really need to make sure that the system is running. You need to do testing. You need to have some unit tests for this. Well, unit tests, maybe not so much, because sometimes when you do this testing, the machine will reset, and that's not great for running your automatic test bed. It's a machine that spontaneously resets in the middle. So So how do you test this? Well, one way would be to send a cosmic ray at your RAM. Unfortunately, suns are kind of hard to steer and to aim. They're like this big orb in the sky, and you can't really push it or point it somewhere, and so it's a little bit difficult. You could hold an alpha emitter up to your RAM, and that's, I mean, maybe that works, but it's like there's this incident in 2006 where that really put a damper on the market for polonium-210. It's really hard to find these days. Now, I guess there are other alpha emitters you could use. You could maybe open up a smoke detector and use some americium. There's a little bit in a lot of smoke detectors, and maybe that'll work for this. I haven't tested it. If you do, let me know. I'm curious to see how it goes. I like to hear about science like this, but.
It does work. People build batteries with americium sources by decapping a transistor and then basically using it as a solar cell.
So yeah, it's possible. If you want to do that and put some shielding around your americium and hold it up to your RAM and check to see what happens. Okay, right, yes, because I guess you need enough of an alpha emitter to get past the standard shielding in the DRAM to begin with. So you could use an EMP. Like there's this thing on the market called a chip shouter. I haven't tried it out. This is not an endorsement of it. It cost over 6,000 Canadian dollars at Mouser anyway. And when I looked into it earlier this week, it wasn't going to ship before BSD can. So it's a little bit yeah. So if you want to send me one, I'd be happy to try it on some machines. Or if you want to buy one and try it yourself, report back to me. I'm very curious to hear. You could also use row hammer. How many of you have heard about row hammer? So this is a technique of writing or issuing memory transactions in a particular sequence, hammering on the DRAM, flushing the caches in order to try to corrupt the memory somehow. It was devised as a way to attack software in bypass software security mechanisms. But in principle, it would also work to check what happened, to detect reporting of memory errors. Now, there's also some row hammer techniques that bypass certain EDAC systems, because this is an intelligent adversary again. But it's kind of annoying because you have to do science on your particular DRAM module or your DDR controller and CPU and stuff. And so you read the papers in row hammer, they go into a lot of technical detail about this one particular AMD CPU with this one particular DDR controller with this one particular DRAM module. And is that going to work on your laptop? No, probably not. You've got to find a different one. Now, an adversary trying to break into your laptop might be motivated to do that, but if you're just testing your RAM to, testing your system to see if you get EDAC errors, well, probably not that motivated to figure out a custom row hammer attack for your hardware. The last option is error injection, and well, not all the hardware supports it, but if your hardware does support it, then it's the easiest way to verify that your software and hardware stack will report an error back to a log that you will notice to detect that there's something going wrong with your system. So, in principle, the way it works is you write to some hardware register in the memory controller, and then an error comes flying out of your system, log whatever, as if it were a real error, and you confirm that it works, and you move on to something else. And this is an ideal. This is how you hope it works. In practice, well, there are some snags. So when you inject an error, often it comes out as it will come out as an error reported in some address some address in memory that gets reported to the operating system. And if the operating system then wants to consider, say, recoverable versus fatal errors, it might try to see what's going on with that page, that address, the page in that address, and then maybe kill a process. Or if the address is in kernel memory that it is not some process it can just kill, well, maybe it's going to crash. And it's kind of annoying if you're running an automatic test bed because you don't want your automatic test bed to just have the kernel crash when you're running your unit tests. And in some cases, you don't even have a choice about what address it happens in. It's just the next memory transaction issued by the CPU or anything else in the system will get an error when you enable an error injection. So if it's a parallel multi-core system with I/O happening, then maybe it's some DMA engine is doing DMA into a buffer into your kernel NFS stack, and then bam, gone. The system crashes. It's a little annoying. And then sometimes what I found is when I tried to inject a correctable error just to see, this should be harmless, right? Injecting correctable error, I just want to see a log message, verify that I push the button and a log message comes flying out. But if you inject a single bit error in the right or the wrong places, it might turn out to actually corrupt the memory. It's as if you just flipped a bit yourself in that memory and then triggered the logging process. So a workaround that I found for the hardware that did this was to inject an error in the parity bits rather than the data bits. Somehow, the designers of the system decided that, well, yep, so if you inject an error, then it's just going to flip the bit. And so if that's in the data bits, then it actually corrupts your memory. But if it's in the parity bits, then the DDR controller will say, oh, there must have been a single bit error here. Let me correct the error, and then put it back to what it should be. That was a frustrating debugging session. And then sometimes we'd inject an error, a double bit error, uncorrectable error, just to make sure that when the system crashes, it leaves a log message in console message saying this was a memory error, not just spontaneous reset. And it just stopped responding. And so I said, OK, that's interesting. Let me try reset and reset over the ILO, and no, that doesn't work. OK, let me try logging into the thing and doing a remote shutdown, remote power up. Silence. Machine doesn't come back. I had to go across into the lab, across town into the lab, and unplug both redundant power supplies and plug them back in before the machine came back. Somehow, injecting a double bit error into the system caused some persistent fault in some firmware, some part of this elaborate firmware stack that prevented it from even booting again. When doing a cold shutdown and reboot, had to actually remove the physical power supply. I mean, I could have rigged it up to a remote controlled power switch rather than the ILO power supply, but I didn't have that at the time for this machine because why would you need that? You can remotely shut down and power up with ILO, right? So I mentioned that there's a lot of DDR controllers with super secret, vendor secret, NDA covered documentation, and it's annoying when you run into those. But fortunately, on most big server class hardware these days, with x86 and ARM at least, if there is support for reporting errors, memory errors, then it is exposed through a standard interface called APEI, which is a gigantic extended TLA soup consisting of the BERT, the HAST, the ENG, the ERST, the boot error record table, hardware error source table, error injection table, and error record serialization table. You can check whether your machine supports APEI by looking at the ACPI dump-DT output, whether or not your kernel will do anything with it. So in NetBSD 10.1, for instance, you'll also see it in dmessage, but in earlier NetBSD 9 or in other systems, I don't think OpenBSD supports APEI, so it's not going to show up in dmessage, but it will show up in ACPI dump. And you can browse through this megabytes of output to look for one of these 4 keywords: BERT, HAST, ENG, ERST. Helpfully, it doesn't actually say the letters APEI anywhere in here, so you have to know all 4 of these acronyms. And there's a standard interface that is very elaborate and covers a lot of situations, a lot of types of errors, a lot of types of error sources, and so on. Here's an example of what the dmessage output looks like on NetBSD now. This is on a server that will that has just a small amount of error detection and correction for the RAM. There are other sources, so you might see some machines with like PCI error detection and correction, PCI EDAC, or CPU cache EDAC, or something like that. This machine just has memory EDAC, and it reports that it can. Right. So it reports that there were no errors between when power was initiated and when we got to the demessage part, and it supports injecting of correctable errors and fatal errors, and it supports a persistent log with the ERST of 8 kilobytes, and then there are 2 hardware error sources, the HEST. So the BERT, boot error record table. This provides error reports for early at boot before your OS is even started. So before you have a chance to set up an interrupt handler that logs errors. It will persistently record them from the boot time until you get to the point where you can check, were there any errors at boot, and then act on them. So it's by the time the OS boots, it is statically initialized and is not going to change anymore. The HEST hardware error source table lists the sources of errors that will dynamically report or that you can dynamically query as the machine is running. And this is the most interesting table for actually getting the error reports. So as I mentioned, this not just memory errors, but also PCI errors, CPU cache errors, CPU register errors, interconnect errors, whatever. Yeah, so you might use the sources in this to the information in this to decide, if you get an error in memory, well, you disable that page of RAM, kill any process involved. If you get an error in a PCI device, then you might say, well, this PCI device is no good anymore, but maybe it doesn't matter. Maybe you're not using it. Maybe it's, maybe you have a multi-GPU system and you have a bunch of VM guests that are all using, sharing these GPUs, and well, one of the GPUs goes out, you can still run the other ones. Here's an example of what the ACPI dump output looks like for a hardware error source table entry. This is an error notification that will come in through a non-maskable interrupt, NMI. And so this is what your NMI handler will query to see, was this a memory error when you get an NMI. So you don't just say, unexplained NMI, gronk. You might say, well, this is a memory error. Actually, no, I guess this is just telling you that the CPU might get an NMI if there is a memory error. The generic hardware error source table is where most of the errors will be reported through. There's this elaborate data structure with pointers to an elaborate data structure with pointers to an elaborate data structure, because this is ACPI. We can't have a simple few bits here. This tells you this is mostly about memory errors, but you can look at the ACPI spec if you care about the gory details. There's a lot of stuff in here. I guess the one interesting thing is this entry tells you that you have to poll some memory location to check if there were errors, as opposed to an NMI, which actively synchronously notifies the CPU. Sometimes you'll get like ACPI notifications at a lower priority interrupt than the NMI, but this example of an error source is polled. So you set up a call out that runs every minute to check was there an error or something. This even suggests the polling interval, which is every minute. There you go, 60,000 milliseconds. ENG. This one is fun, and of the BSDs, I think only NetBSD does anything with this. This is how you inject errors to test that things work, which is very important to do before things start to crash and burn. So the ENG is a list of supported error injection actions. So if you want to inject an uncorrectable error at some address, you may have control over the address, you may not, but that's one of the actions you can do. And so just table these actions. Well, sort of. It's not quite a table of actions. It's actually an interpreter for a programming language of supported error injection actions. So the OS can write a program with a sequence of actions that the ENG table will interpret to actually do the error injection. Actually, that's not quite right either. It's a programming language for an interpreter for a programming language for an interpreter of error injection actions, because there's these series of low-level operations of like reading a register, writing a register, looping. I forget whether there's loops actually, but you can certainly jump forward, and these are the operations that are used to implement the high-level actions that the operating system will execute in order to do an error injection. ACPI. So the actions that the operating system can do are to like begin an injection operation, set the error type to be like memory correctable or memory fatal or something, and then set error type with address. Some machines support injecting at a particular address, which is great because you can allocate a test page and then have an error in that test page, and then you don't have to, worry about accidentally blowing away some kernel data structure when you're doing your tests. Unfortunately, not all hardware supports this. And then when you set up the error type and address and any other parameters, you hit execute operation, and then check the busy status and get command status to find out how the injection completed. Did it complete? Did it succeed? Did it or not? And then you have to trigger it with the trigger error action table, which is a meta action that actually points at another table of actions. It's funny, ACPI has this, this whole, interpreted language of methods that you can call to query device stuff. It doesn't use any of that whole ACPI bytecode thing. It's this entirely separate little programming language for interpreters of programming languages for. And the instructions at the lower level are like read register, and compare with an immediate value. These are like CPU instructions. This is the sort of the assembly language of these error injection things. And here's what an error injection table looks like, sort of. It's for each action, there's a series of instructions with some instruction parameters. And so to execute an error, set error type action, for instance, you have to do write register value, write register, read register, and then write register, according to this table. In principle, it can be interleaved. I haven't seen this in practice, but the spec doesn't prohibit, as far as I can tell. So you might have different actions in different orders with the different instructions. I don't know. Here's what it looks like in ACPI dump output. So this will tell you what error actions are supported on your hardware. I already skimmed through this. The ACPI ERST, E-R-S-T, this is a little persistent storage in the firmware. You might use this, for instance, to store error logs or store dmessage. It is, well, okay, it's not a persistent store. It's a little programming language for storing files persistently. Except, well, actually, it's an interpreter for programming language for. Somehow, it's kind of amazing how many levels of interpretation are going on in this ACPI firmware interface. And there's even more operations for actions for the ERST, because it's about reading and writing files and data and sequence of records and listing the records and stuff. And there's this really elaborate little instruction set for how the actions are implemented on each particular machine. You've got go to, you've got add, subtract, skip next instruction if true. You've got conditional branches. It's really elaborate. This is what it looks like in ACPI dump output. It isn't completely bonkers to have this little instruction set for the error record serialization table, where you might store logs persistently so when you reboot, you can get back to the logs, because the errors might happen in really nasty contexts. You might run in, you might want to record dmessage or record some error log when you get an NMI. In an NMI, you can't touch interesting data structures. You might not want to run the full ACPI interpreter. So it's not totally bonkers that it has this elaborate level of abstraction to programming languages and interpreters and stuff. So in Linux, it's exposed via a file system called pstore. NetBSD doesn't use it yet. I don't think any other BSDs use it. I know FreeBSD has an API driver, but I don't think it uses the ERST. So in NetBSD, as of last year, we have an API driver. It's enabled in x86 generic kernels since 10.1, maybe soon on ARM too. Needs some more testing. And it supports detecting reports from many common error sources. The generic hardware error source is the main one for memory errors. There's a crude interface to sysctl interface to ENG, and there's code to implement the ERST interpreter, but nothing uses it yet. So we haven't implemented a persistent file store using that. Now I think I'm running out of time, but if I have a moment, I'm going to try to do a live demo if I can. Not on this laptop, but on a server far away. Just a sec. Gotta get connected to it. I had this all set up, but then the connection died while I was talking. Okay, let's see. It's going to work. Oh no! Of course, as a live demo, everything has to go wrong. There we go. Oh, come on. There we go. Okay. So I should probably make this bigger, shouldn't I? Probably can't see this very well. Nope. Okay. There we go. Okay. All right. Is this visible? Yes, this should be visible. So let's inject a single bit error. So I'm going to run the sequence of sysctl commands. This isn't really wired up very nicely, but it works enough for testing. So this runs a bunch of ENG actions in sequence once I hit return, and oops. There we go. We've got a memory error, single bit error, corrected from issuing memory error injection through APEI. Now this is a correctable error. I can also inject an uncorrectable error, but then my machine will have to reset, and which is a little bit annoying. So maybe I'll I don't know. Should I do that?
Sure.
All right. Okay.
How friendly are you with your smart hands, people?
Okay, so inject 2. This is so the critical difference here is this error type. It was 8 before, 32 this time. These are magic numbers for the APEI interface to set the 8 is correctable if 32 is fatal. All right. Let me have a console open for this. Actually, let me open this in another Emacs window so I can make it big. All right. And of course, this isn't going to work now. Wait. Okay. There we go. I had a previous shell session open already. Okay, so let's get open. I know. Okay, not using shared SSH connections. I got a bunch of SSH connections open so it would all work, and then the connections died. OK, now let's see if this serial console works in Emacs, which I haven't tested. Ah, there we go. OK, cool. All right. Let's, here's the injection going. And let's look at the console. Oh, there we go. It just crashed. And it showed the error, and now it's dumping core. And it's going to dump core for a while. It's got the 100 gigs of RAM or so. It takes a few minutes to dump all the core. All right, so any questions?
Did you say whether the condition you observed, whether it was a hard...
Oh, wait, hold on. Can you wait for the microphone so the video audience can hear?
So the condition that you originally proposed in here, was that, did you say whether that was a hard error or soft error?
Oh, you mean the
when you did the get status?
the get status thing?
Yeah.
That was a hard error in the DRAM.
Okay.
This is come on. This so this error here. This was so. The DRM turned out to be bad. I was able to determine that by running the full extensive Lenovo diagnostic tests on my laptop for several days. Not just that, but I open up the laptop, take out one of the DRM modules, run the test on the other one. It takes like 24 hours to run the full tests, and then swap them. And one of those had persistent, had. I mean, I don't know if it was the same bit positions in the RAM, but it kept reporting errors in this diagnostic test. So that's why I sent the RAM back to the manufacturer and got a replacement, and that's the replacement is what I'm using now in this laptop right now, and I haven't seen anything like this since then.
Thank you.
Hey, interesting presentation, thanks. I'm curious if you looked at something like QEMU to maybe implement ability to inject those errors.
You're wondering if QEMU supports APEI and error injection from the host?
Yeah, but
I have not looked into that, but that is a good idea, and that would make it more convenient to test some things, especially if you don't conveniently have access to hardware that does error injection, or you don't want to reboot your server that takes several minutes to come back up every time.
yeah, and you obviously have more control how you inject it, so you're not constrained by whatever
Yeah, so the constraint is, well, I guess with QEMU, you can, in principle, you could implement whatever kind of error reporting you want, but someone has to do the work to write up create the APEI tables and connect it to a device register that is emulated by the QEMU, and then if you did that, it would be ideal to just implement APEI as is and not implement any new interfaces for QEMU, because the interface is already there, APEI, and it's flexible enough that you can APEI supports expressing pretty much any error injection you might want to do. But a lot of hardware doesn't support all of the options. So with QEMU, you could add all the options you wanted. It's just a lot of work to do that. I don't know if anyone's done that yet. I hope they have, but if they haven't, then maybe that's a nice project to do.
Oh yeah, anyway, some idea, good.
Other questions?
I'm wondering if it will be possible, or if you plan to make it possible to decide what to do on uncorrectable errors?
Yes, that is other future work. I think so some systems already support this. So I used to work at VMware, and at VMware I don't know how much control there is over it, but one of the features that it publicly supports is killing a VM guest and leaving the other ones to run, if possible, if you can attribute the page to that one VM guest. So similarly, in NetBSD, what I would want to implement, which I haven't done yet, is connect it to the UVM system and find out is this page used by only one process or by some processes or by a NVMM guest or something? And then you kind of a sysctl knob to tweak the choice of action here. Do you just crash the whole system? Do you kill the process? Whatever.
And then the follow-up, complementary to this, would it be neat to implement a way to have maps of bad memory to not use in case?
Oh,
you
sure,
wanna
sure, yeah.
keep-
So, if you get a bunch of bunch of correctable errors in a single page of memory, then yeah, you might want to have the VM system say, that page is suspicious. Let's kick that out and not use it anymore. So that is also a reasonable thing to do. Of course, you need to have some policy. What's the threshold? If you get one error, probably don't want to kick out a page. If you get 1,000 errors, yeah, maybe you do want to kick the page. What's the cutoff? Yeah, so you need to have some parameters for that and some practical experience with it. Again, not implemented yet, but that's a good idea and should implement it. Hold on, there's a. Can you pass the mic down?
Very reminiscent of the bad block mapper that we had to
Yes,
use back
yep.
in the day of old hard drives.
Yes. So yeah, you can have bad blocks of DRAM just like you used to have bad blocks of
I mean,
disks.
and the attendant other problems. I mean, if you map this block bad, then you have to figure out what to do with the file system and tell it how to ignore that as well. And
Yep. Yeah. So for a single boot, it's very easy. You just store data structure memory saying this page is bad. Don't do anything with it. If you want to save it across boots, that's you got to deal with some persistent state there and some management of the state, and so yeah, that might be an interesting project to pursue. Other questions? One more up front. Can you pass the mic up front here?
Okay, so I'm wondering if OpenBSD's weird memory randomization thing makes this better, worse, or harder to diagnose, or anything like that.
You mean ASLR, KASLR?
Yes, those letters that are yet more
Just
four-letter
basically
acronyms.
randomization in the kernel? Yeah. I mean, what it will do is if you have a hard error, that is some particular page, some particular word of DRAM is persistently bad, without KASLR, you might get the same crash repeatedly. With KASLR, you get an exciting new crash every time. Or exciting new memory corruption, and just you commit the bad thing to Git or Mercurial or whatever every time. Or the document you upload is corrupted. It's a different one every time. So yeah, it's not going to help with detecting any errors, but it might make the symptoms more exciting.
Thanks.
Other questions?
So I noticed some weird characters in your slide titles. Are those deliberately injected single-bit flips?
Well, they are all single-bit errors, so they are all correctable. I will leave correction as an exercise to the reader.
It's interesting how the brain automatically.
Some of these are broken. I don't know which ones. Oh, here we go. These are, I guess I should say, single-bit errors in ISO 88591. They might not be single-bit errors in, in EBCDIC. Any other last questions? I think my time is running. Well, I guess I'm holding you up from lunch, so. But if any other questions, I'm happy to take them, or I'll be around. Thank you.